Lab update, Monday, February 9th, 2026. We identified a bug in the G-EDM pulse board where the voltage output was oscillate around its actual value at around 3 MHz, causing a lot of noise in the signal.
I slowly bring up the voltage to, like, let's say 30 volts. You can see it seems to oscillate in a triangular manner. Increase the voltage, at some point it's gonna, at like 49 volts, it turns into a line, and now if I decrease it again, now it stays a line.
And we've discovered that this is just simply a missing capacitor in the feedback path of the final op amp.
The blue circuit is the old one, the yellow is the new one.
If we look at the last op amp in the signal path for the feedback signal, you can see that there is no capacitance in the feedback path, making this op amp basically just run at whatever frequency it can. And as it gets to the higher frequencies, any noise just gets amplified and starts oscillating. So just adding a small capacitor here of around 3 to 10 picofarads fixes this problem completely. In the process of doing this, we also measured some of the signal path and found out what its actual filter characteristics are. And we have this here. We can see there is the gain response. The gain stays pretty flat until we get to around 80-90 kilohertz or so, where the minus 3 dB cutoff point is. So this filter has a bandwidth of around 80-90 kilohertz, which is far away from the opto-isolator's maximum bandwidth. And we can see like what this does to signals. Like here we can see a 20 kilohertz, 25% duty wave gets like quite significantly smoothed, and at 50 kilohertz, the same wave, it's basically just like one sharp spike and loses all resolution as well as what the actual voltage is. So we discovered the bandwidth limitation of the existing signal path. In the process of trying to fix this error, at first we thought there was something more significantly wrong, as the circuit is very different from the recommended circuit of the datasheet. We redesigned the signal path and got it working much better. We managed to build a circuit slightly modified from the datasheet that can achieve near 1 megahertz bandwidth with very high linearity, and we got this working pretty well. So we'll definitely document how that works. We've, however, decided as the fix is so simple, we will not redesign the complete signal path, as that would also require changes to the firmware and would cause problems with backwards compatibility. Just adding a single capacitor seems a lot easier, since that can fix like all previous revisions as well. And I will still, however, try to get some documentation about this new circuit. In case anyone wants to build a new design, they can very much use that. We've also gotten around to assembling the motion board, so we'll have the brain as well, and we can actually build up a whole system. We now have the motion board and the pulse board fully assembled. We have the screen. We will have to build a shunt, and then we can flash the firmware onto the board and see if it actually sparks this week. So this is going to be pretty exciting. In the process of building the motion board, I got to use one of my JBC tips I found on storage, which is a very wide tip for soldering pin headers. And wow, that's really amazing.
The soldering iron tip goes so hard. Boom.
Usually I just go with like a bent conical or a bent chisel tip for my soldering, just for more mobility, but this is super useful for pin headers. On the oscilloscope, I mentioned a few crashes last time, and I've managed to update the firmware to version 1.05, I think. And that was a bit of a challenge, since the internal update tool just said there was no new version available, so I had to track it down manually. But this update has fixed all the crash issues. I can now use bode plot with no problem and XY mode, and nothing crashes anymore, so that's very good. I am quite happy with it now. I've also interacted with it over the network using both the SCSI as well as the web interface from a script, and that works very well. I managed to automatically capture test images at different frequencies, so I can quickly test new revisions of boards and then apply different waveforms at different frequencies and take screenshots. So I just run a command instead of having to measure 10 different settings and manually entering all those, which has significantly sped up development, and I can highly recommend this. I would always go for network connected equipment when you can, because it's just so much easier to then connect those for automated testing or synchronize between multiple devices. And a simple Python script can control most devices relatively easily. I wanted to thank you for all the views and nice comments you've left on the last video. That was really nice. I really appreciate that feedback, and I hope you enjoyed this video as well, and I hope I can produce some more good tutorials in the future.